All right, here are our solutions for quiz 4 from Math 251. We're given three curves here. Maybe I'll label them A, B, C. And asked, I'm not going to label them A, B, C. Yeah, I'm going to label them A, B, C. Why not? And said that one of them's told that one of them's a function, one's the derivative, and one's the second derivative, the derivative of that derivative. And asked which is which. Okay, well, a couple ways you can get at these. Something I like to do is look for spots where a curve is flat. So like if we take this green one here, note it's flat right up here. So if the derivative of this curve here, this green one is pictured, the height of that curve better be 0 at this point right here. Similarly, it would have to be 0 at this point, right? The points where the green curve is flat. It also looks pretty damn flat over here and over here. So the height better be 0 at a lot of different places if the graph of the derivative of this green thing is shown. Well, blue doesn't have a height of 0 right here, and red doesn't have a height of 0 right here. So what that tells me is that the derivative of this thing C is not pictured. If the derivative is not pictured, C can't be f or f prime. In other words, C must be equal to the second derivative. Okay, so if this is the second derivative, that means this is the derivative of one of these two curves. The question is, which of these curves has this weird thing as its derivative? Well, we can rule out A pretty quickly, because if you look at A is always increasing, right? It's going up the entire time. The speed at which it's going up changes a tiny bit, but it's pretty much going up the entire time. So if it's going up the entire time, that means its derivative would have to be positive the whole time. This thing right here is not positive the whole time. It's negative down here. So what that means is that green is not the derivative of red. What about blue? Well, blue's positive the entire time. So blue might be the derivative of red. So what I'm kind of starting to think here is that A is my function, B is its derivative, and C is the derivative of that. Let's see if we can talk ourselves into this. If A is the function, it's going up the entire time, so that means its derivative should be going up the entire time. Looks like it's a little bit steeper in here. Right, it's going up kind of slowly, and then it gets a little bit faster, and then it slows off again. It's exactly what B does. Its height is about the same, and then it gets big for a minute, so it's a little steeper, and then it goes back to normal. Normal speed, fast, normal speed. Yep, B is definitely the derivative. Well, that's not what I wrote. B is definitely the derivative of A. Is C the derivative of B? Well, let's see. B is pretty damn close to flat at the start here. Maybe it's going down a tiny bit, but it's almost flat. So what that means is derivative should be almost 0, maybe slightly negative. It's exactly what green is. The height here, slightly negative, but pretty damn close to 0. And then it turns and it decides to go up for a little while. So if it's going up, that means its derivative should have a positive height. Note the height of this green graph is positive all throughout here. It's positive all the way until we get to this point right here. Note that this is the point where blue stops going up and it starts coming back down. When blue starts going down, the height of green better be negative. Yep, green's negative all throughout here. And then finally, right around in here somewhere, blue flattens off and gets pretty close to flat, which means green should get really close to a height of 0. Yep, that's exactly what happens. There we go. This must be the answer. I don't want partial credit, so I feel like I'm not going to write why these are. Below is the sketch of a function g. Sketch an approximate graph of g prime. All right, things you'll want to make sure that happen. The height of my derivative g prime better be 0 right here. That's the key thing. It's flat right here. The height better be 0. To the left here, this thing is going down. It's going down pretty fast, and then it starts going down slower and slower and slower until it gets to 0. But the point is it's going down all throughout here, which means the height of the derivative better be a negative number all throughout here. It's steepest here, so it's the most negative here. It gets less and less steep as we get to this point, so the height of this gets closer and closer to 0. And then we hit this point, and it turns around and starts going up. So if it starts going up, that means the height of this thing better be a positive number. And it starts going up faster and faster and faster until we get to this point. So until we get to 2 here, it's going faster and faster and faster. So what that means is this height is getting bigger and bigger and bigger. Let's get it something like this, and then draw an open circle. Why an open circle? Because at 2 right here, the derivative is undefined. Right, we have this sharp turn, so it's undefined. To the left of 2, it's pretty steep, hence this height is pretty high. To the right of 2, it looks like it's linear. Up 2 over 2, it looks like it's linear pretty damn close to 1. So what that means is that the height should be really, really close to 1. I should put an open circle at a height of 1 and say, yep, it stays at 1 the rest of the time. Function should look more or less like this. I don't really care about how you curve this thing. There's really no way that you should know that it kind of does this little weird loopy thing. In fact, it might just be linear. It's really hard to tell. I'm going to draw it linear. So there's no reason that you would know that it looks like that. So I'm going to go back and fix this a little bit. I'm going to just do the exact same thing I said, but without kind of the more subtle things. Let's do it something like this. This is very approximate, but the point is you want the height here to be further negative than it is when it gets close to 0, and the height at 0 better be exactly 0. That's key. And you want this open circle to show that you understand that it's not differentiable here, and then I want you to recognize this is linear, so this height stays constant at 1. Hit those things, you got everything I want. All right, finally, the last problem, I guess. It says the below curve is the derivative of a continuous function h. In other words, h prime is shown. So this is h prime. This is not h. This is not my function. This is my derivative. That's what I'm getting at here. Answer the following questions. When is h decreasing? H is decreasing when h prime is negative. Right, if your derivative is a negative number, that means the slope is negative. In other words, it's decreasing. Okay, so where is h prime negative? Well, here is h prime. It looks like it takes on a negative value everywhere from -4 up to -1. And then again, maybe I'll put and. From -1 all the way up to 1. What I'm saying is the height is negative all throughout here. Here it's not technically negative. Here it looks like it's 0 to me. So I'll take out that point. And then again until I get to here. And then I'm even going to put parenthetically if you include -1, that's okay. But this right here would be my answer to when this function is decreasing. Now it says, when is h concave up? H is concave up when h double prime is positive. That is, in other words, not or, because it makes it sound like either of these things can work. I'm going to say, in other words, when h prime is increasing. Okay, maybe that deserves a little explanation. If h prime is increasing, then since h double prime is the derivative of h prime, think about this as my graph. If my graph is increasing, then that means its derivative is positive. So what I'm getting at is h prime is increasing means h double prime is positive. If h double prime is positive, that means we're concave up. So to figure out when this thing is concave up, what I have to do is look at h prime, because that's what's given to me, and figure out when it's increasing. Well, let's see, if you look up at your graph here, it looks like this thing that's given to me, h prime, is increasing in 2 different spots. From here to here, right? It's going up from here to here. So -3.1 to -1, maybe. But then there's another spot where it's increasing. Starts somewhere in here and it goes forever. So what is this? An x value of about a half? Maybe a little bit less, maybe a third. It's called 0.3 all the way up to infinity. So what I'm saying is this graph that's given to me, h prime, is increasing in these two different spots. But I know that when h prime is increasing, h is concave up. So the answer to the question about when h is concave up is on these two intervals here. All right, finally, the last part says to find the x values on which h of x has a local maximum and which h of x has a local minimum. Okay, so for h of x to have a local maximum, the way I think about it is the graph has to look, roughly speaking, like this at some point. This right here is a local maximum. And so what properties, what's going on here? Well, the derivative is going from positive to negative, right? If we're increasing and then decreasing, to get to the top of the hill, you had to walk up the hill and then walk down the hill. We must have been increasing and then decreasing. Well, increasing happens when the derivative is positive, and decreasing happens when the derivative is negative. So what I'm saying is we get a local max when h, not f, changes, when the derivative changes from positive to negative, as you read it from left to right. Used to be going up, now you're going down. That means you had a local maximum in there. What about local minimum? Local minimum is very similar, except now it's when the derivative changes from negative to positive. Same logic. To be down at the bottom of a valley, you had to walk down a hill, and then you'd have to walk up the other side of a hill. I don't know, negative to positive. So what I'm saying is we can figure out the local max and local mins of a function h just by looking at its derivative, h prime. If we can figure out the spots on h prime, where h prime used to be positive and is now negative, what we will have is a local max. So you go up here and you say, well, h prime was given to me, and it's positive here and here, and it's negative all throughout here. Maybe it's 0 at this point, kind of hard to tell, but it's certainly not positive. So for a local maximum, well, let's see, we said local maximum happens when your sign changes from positive to negative. Well, it looks like at this point right here, -4, our sign changed. It used to be positive, now it's negative. So what that means is h of x has a local maximum at x equals 4. Local minimum, well, that happens when the derivative goes from negative to positive. Well, the derivative is negative when we're to the left of -1, but it's positive when you're to the right of -1. So at this point, -1 right here, my derivative switched from negative to positive. If my derivative switched from negative to positive, my function had a local minimum. So my function has a local minimum at x equals 1. So I guess that's it. I don't know if that even needs a box. I'll leave it at that. So that's the end of this quiz. I'll stop the video here.